Hello, everyone. I'm Rong from Nanjing University. It's quite a great honor to be here to present our work. It is titled Meces, Latency-efficient Rescaling via Prioritized State Migration for Stateful Distributed Stream Processing Systems. This work is jointly done by Rong Han, Weichang, Zhong, Chunfeng, Yuan, and Yihua Huang from Nanjing University. In recent years, stateful stream processing engines, or short as SPEs, have been widely adopted because of the increasing demand for complicated analytic over real-time data. For example, the frag detection, log monitoring, sentimental analysis, and IoT applications. SPEs are expected to be long-running and always have low latency performance. Therefore, it commonly requires SPEs to perform dynamic rescaling in the face of unpredictable circumstances. For example, the data rate fluctuation, machine failures, processing stragglers, and so on. However, other processing operators in SPE are usually stateful and partitioned across workers. Rescaling them calls for state migration, which means moving data between workers, even across networks. Major advances made in this area in last decades can mainly be classified into four categories. The first one is the full restart approach. It pauses and resumes the whole task when with distributed states. The second one is the partial pause approach. It restarts a subgraph instead of the whole job topology to reduce the extreme blocking. However, both approaches they block the processing of SPE. They usually cause latency spikes during the scaling periods. The third kind of approach is called a replicated data flow approach. It executes a new data flow in parallel with the older one until finishing the state migration. Therefore, it usually results in high resource usages during the scaling. The last category is called a proactive approach. It adds extra behavior to long scaling stream processing periods to relieve the pressure during state migration. It can smooth the latency curve during rescaling, but due to this design, it needs to incur extra overhead to a long scaling data flow. In conclusion, existing state migration approaches suffer from latency spikes or high resource usages or major disruptions. As discussed in this paper, existing approaches' common limitation lie in order unaware state migration. That is to say, they do not take into account the order in which operator state migrates. Here, we use an example to illustrate how the migration orders affects SPE latency performance during rescaling. We take a representative stateful stream processing job, key count, as an example, where the records with random keys come from upstream and are processed by SPE in a FIFO manner. That's the first come and first out manner. In this case, stream operators store and the count value of each key as their corresponding states. Now, during the scaling, C1 needs to migrate keys 1, 2, 3 to C3. For correctness of processing, an affected operator needs to receive the migrated states, which are the global counter value of the keys, before it can process the corresponding incoming records. If the states are migrated in an unaware manner, the first coming record may not be processed in time, because it needs to wait for the arrival of its corresponding state. This also blocks subsequent records in the queue due to the FIFO processing. Eventually, it will accumulate the processing latency for all records over a period of time. In the worst case, as shown in subfigure B here, the state of the first record is the last one to be migrated, blocking all record processing before the state migration is finished. Ideally, as shown in subfigure C here, states are migrated in exactly the same order as the records arrive. Therefore, minimal time is spent in the waiting queue, and the latency can be gradually reduced. From this observation, we can find that when online migrating states in SPE, there are actually hotkeys, which refers to the keys that are being processed or about to be processed by downstream operators' tasks. We find that the state of hotkeys need to be prioritized so that the stream processing proceeds without blocking. Based on that, in this paper, we propose Meces, an on-the-fly rescaling mechanism which enables prioritized state migration for SPEs. To achieve that, one challenge is to dynamically adjust the state migration order according to the incoming records during SPE rescaling. To address this issue, Meces leverages a fashion demand state access model. During scaling, the state can be actively fetched by SPE operator instance when receiving a data record whose state is not local. Another challenge is to maintain the state consistency during the prioritized state migration process. Therefore, inspired by previous works in Meces, we use a coordination protocol based on controller messages. Next, we use an example of a scale-out operation of a stream key count job to illustrate the above design for rescaling periods in Meces. In this example, the degree of parallelism of the count operator increases from 2 to 3. For simplicity, we assume the keys are between 1 and 12. Therefore, based on the uniform distribution, the distribution of the key space before and after the rescaling is shown in the right subfigure. We call the time period from the beginning to the end of the state redistribution as a migration stage. The global controller of SPE starts a migration stage by injecting a special data record called a controller message into the source operator. The message then travels through the whole pipeline in the same way as a regular data record. When S1 or S2 receives the control messages, it updates the routing strategies and outputs the subsequent data records in accordance with the new topology. As its downstream operator's degree of parallelism will increase by 1, its new strategy divides the key space into 3 parts equally. We can see the demonstration here. Okay, as I show here, the records mapped to line or previously sent to B, but will be shipped to the new instance C from now on. Meanwhile, the record with key 6, which were consumed by A, should then be in charge of B, As for the count operator, in general, the states are set from the previously responsible instance, but the newly responsible instance also actively fetch states in response to the incoming data records. Taking B as an example, when B first receives a control message, such as from S2, it can foresee the arrival of the keys that did not belong to it before. After that, when B encounters a record whose key is not local, such as key 6, B borrows the corresponding state of this key from other count operator instance to complete the processing. We can see the demo here. Okay, note that in this phase, the message from S1 has not reached B, which means A may still have to deal with records with key 6. Because of that, B should also be prepared that its state of 6 can still be brought back by others. The migration for B is aligned once it receives control messages from all of its input channels. You can see the demo here. Okay, in this situation, it is guaranteed that all future records with key 5 and the key 6 are shipped only to B, and B will no longer receive records with keys from 9 to 12. Therefore, B can start its state migration. It sends the state between 9 and 12 to other instance, and fetch from states in 5 and 6 asynchronously. When finishing sending and fetching, B sends the completion signal of its migration stage. In the above process, we can maintain exact one semantics during migration stage, and the stream processing operators keep functioning without explicitly blocking the input channels. In addition, as the fetch-on-demand model calls for lightweight state accessing, we also design for fine-grained state transmission. In Meces, during scaling, we further divide each key group into multiple subgroups. When encountering a record that requires a remote state, an instance tries to fetch the corresponding subgroup of the record key instead of the entire key group. This reduces the overhead used to obtain the data that is not needed immediately. We also achieve fine-grained migration via gradual migration strategy, which splits the update into several micro batches of state migration. So the single migration stage is split into several gradual fetch stages. In this way, we affect only a tiny proportion of the entire states at each gradual fetch stage, where most of the records can be processed normally. We implement the Meces on top of the mainstream open source SPE, which is called Apache Flink. Meces is implemented without affecting non-scaling periods. The underlying state management and migration in SPE runtime are completely transparent to user codes. Therefore, it takes minimal effort to switch between Flink's and Meces state implementations. We evaluated the latency performance of SPEs during scaling. We compare Meces with native Flink, which stops the whole job when rescaling, and order unaware, which is online block-based state migration without order prior authorization. On the key count job, both native Flink and order unaware show a latency peak which is 3 orders of magnitude higher than Yihua. The latency decreases gradually after the restarting or migration completes. As for Meces, it keeps the latency under 600 milliseconds during the migration stage. We further evaluated on the real-world next mark benchmark suit. Similar conclusion can be drawn from the result. Meces lowers the latency peak by orders of magnitude. We also report the latency breakdown of Meces. Compared with the order unaware, the latency peak in Meces is gradually reduced to less than 400 milliseconds. This is because when Meces migrates states, as shown in Fig C here, the several long-duration execution blocks caused by migration cost are converted into thousands of short-duration fetch operations. Therefore, in Meces, although the sum of the migration cost does not differ much for two strategies, each record indeed does not have to wait for long for its state to be migrated. Eventually, we can reduce the queuing cost and flatten the overall latency curve. Further, we compare Meces with some SOTA works. First, we implement the MacPhone's state migration mechanism on Flink, along with a simplified version of MacPhone's pre-request of SPE. This extra freeze calls for extra synchronization and communication. Therefore, when not rescaling, MacPhone on Flink shows an order of magnitude higher latency than Meces. During rescaling, both systems show a limited amount of latency increase. However, the latency of MacPhone stays at a level around 8,000 milliseconds, while Meces never reached the bar of 1,000 milliseconds. Next, for a fair comparison with Rhino, we implemented the mechanism of Rhino based on Flink. On the key count job, run on Flink shows a similar latency peak to order unaware, whose peak is nearly 10,000 milliseconds. As a comparison, the per record latency of Meces never reaches 1,000 milliseconds during the whole process. Also, run calls for extra network overhead when the job is not rescaling, while Meces includes low network overhead to non-scaling stream processing. In conclusion, Meces prioritize the migration of hotkeys to achieve low latency and resource-efficient scaling in SPEs. In addition, we use control message for state consistency and use low-grounded state management for efficient data transmission. Meces is implemented on top of the widely used SPE Apache Flink, requiring minimal user code modification and low disruption to long scaling periods. That's all for this presentation, and I'm happy to take some questions.